about coordination compounds. So this classification of compounds fall under this subfield of chemistry called coordination chemistry, which is what inorganic chemists study. So I think you are familiar with organic chemistry. So we also have the other field, which is inorganic chemistry. So this subfield of chemistry deals with the rest of your periodic table elements. Organic chemistry deals with carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, and some other elements. While the rest of the elements, they are tackled in inorganic chemistry. And under inorganic chemistry, you have this class of compounds called coordination compounds. So coordination compounds are very interesting. Because most of them involve your transition metals. And since your transition metals have electrons in their d orbitals, they behave a bit differently than your typical molecules. And at the same time, they also display some properties that are unique to them. So in this discussion of coordination compounds, we will start with the introduction, so a bit of a background how these coordination compounds were discovered, and then we will go to their structures, how to name them. So there's a set of rules on how to name these compounds and how to write their chemical formulas. And then we will go to this very special theory discussing the bonding of your coordination compounds, and then we will go to their properties. Have you heard of the color Prussian blue? So this Prussian blue, which was accidentally discovered early in the 18th century, could be the first known coordination compound. So this Prussian blue became of interest to chemists. However, almost a century passed before these coordination compounds became the focus of inorganic chemists. So from the discovery of Prussian blue came so after 100 years, they studied these two cobalt compounds. Okay, so they observed that cobalt, when mixed with ammonia and chloride ions, okay, in particular, if you have cobalt 3 chloride and ammonia mixed, okay, you will obtain this yellow compound. Okay, so if you have cobalt 3 chloride, so that is COCl3. So if you have an aqueous solution of cobalt 3 chloride and you mix it with an aqueous solution of ammonia, you will get this yellow compound. Then the interesting thing about this phenomenon or this observation is that cobalt chloride or cobalt 3 chloride by itself is relatively stable. Ammonia by itself is also relatively stable. But if you mix these two, they form another stable compound, which is this yellow crystals or yellow powder that can be recovered from a mixture of cobalt 3 chloride and ammonia. So since this yellow stable compound is made up of two simpler compounds, they decided to call them coordination compounds. Okay, so because this stable, the yellow powder that they obtained is stable because they were able to isolate it. They were able to get this yellow compound, this yellow powder. And it's made up of two simpler compounds which coordinated to form that stable yellow compound. However, around 60 years later, another another coordination compound of cobalt 3 chloride and ammonia was discovered. This time, it formed purple crystals. It formed purple crystals, and interestingly, when they analyzed the stoichiometry of the elements in the two compounds, they found that for the yellow compound, it combines with 6 moles of ammonia. Meanwhile, for the purple compound, 1 mole of cobalt 3 chloride combines with 5 moles of ammonia. So they performed experiments, very accurate experiments, just to get the stoichiometry of how these two compounds coordinate with each other. So same two compounds, cobalt 3 chloride and ammonia, but they can combine in a different manner. And when they further investigated these two compounds, okay, surprisingly, so what they did was they treated both compounds with silver nitrate. Okay, so they added silver nitrate to aqueous solutions of these two compounds. So that's silver nitrate. And they discovered that for the yellow compound, they obtained 3 moles of AgCl or silver chloride. So from our studies of KSP, we know that silver chloride is a slightly soluble salt. So they were able to obtain a precipitate of silver chloride and then performed calculations to get the stoichiometry. Okay, so they obtained this value. Okay, so that's for the yellow compound. So when treated with silver nitrate, they discovered that the yellow compound forms 3 moles of solid silver chloride. As expected, because we know that there are 3 chloride ions from the source, which is cobalt 3 chloride. However, for the purple compound, when they treated it with silver nitrate, they only calculated 2 moles of solid silver chloride, which is contrary to what is expected because, again, the source contains 3 chloride ions. So there must be something unique to between the structures. Okay, then the structures of these two compounds should be different. In particular, the position, probably we can use the term position. The position of the chloride ions in the structure of these two compounds. So with these results, there's a certain person, his name was Alfred Werner. So Alfred Werner further extended the investigations of these coordination compounds. And he came up with a theory of coordination compounds. So according to Werner, okay, your transition metals contain 2 types of valence electrons. You have the primary valence electrons and the secondary valence electrons. So what is the difference between the two? The primary valence electrons, these are the electrons or the primary valence. Okay, the primary valence is based on the number of electrons the atom loses in forming the metal ion, which means, for example, if we have let's say for example, calcium, right? Calcium tends to lose 2 electrons. Therefore, the primary valence of calcium is 2. because these are the electrons that it easily gives off so that it becomes more stable. Okay? So the primary valence electrons of calcium refers to the 2 electrons that it loses to become this ion. Now, the secondary valence or secondary valence electrons, these are electrons responsible for the bonding of other groups. So we call this ligands to your metal ion. So this means that our metal ions, after losing their primary valence electrons, they have the ability to bond or form bonds with other molecules that we call ligands. So defined here, ligands are molecules or ions that bond to transition metals through their secondary valence electrons. So once this happens, okay, once your um, your metal ion forms this bond with your ligands, you form a complex. So when we say complex, it's a species that involves coordination of ligands to a metal center. Now, going back to our story, the cobalt 3 chloride ammonia complexes, based on the theory of Werner, he proposed that for the yellow compound, the correct formula is written as this. Okay, so it ionizes into this complex of cobalt 3 with ammonia and produces 3 moles of chloride ions. Meanwhile, for the purple compound, its chemical formula is written like this. So remember, the purple compound only needs 5 moles of ammonia. So this ionizes into this complex of cobalt 3 and 2 moles of chloride ions. With this, we can readily see why adding silver nitrate in each led to that observation. Like for the first compound, for the yellow compound, adding silver nitrate will produce 3 moles of silver chloride. That is because this complex or this coordination compound releases 3 moles of chloride ions in solution. While for the purple compound, it produces 2 moles of solid silver chloride because it releases 2 moles of chloride ions in solution. The other chloride is part of the complex, of the cobalt complex. Okay, so this theory of Werner was able to explain a lot of properties displayed by coordination compounds discovered during his time. So when we say complex or coordination compound, this can be a complex cation like what we just saw. Okay, so you can have a complex cation. You have a metal center there, and around your metal center, you have your ligands. It can also be a complex anion. Okay, so you have your metal center surrounded by other ligands, and the total or the net charge of the whole complex is negative. You can also have a neutral complex or a neutral coordination compound. So you still have your metal center and the ligands, but the total or net charge is equal to 0. And of course, you can have a coordination compound. So a coordination compound contains at least one complex. That complex can be the cation of the compound or the anion, or both cations and anions are complexes. That's your coordination compound. Now, you might be wondering, okay, how do we determine the charge of a complex? So, it will be very helpful if you review the typical charges that your metals get after losing electrons. So you have studied it in your previous general chemistry class from senior high school. So for example, iron, your metal iron typically produces iron 2 or iron 3. Lead, lead typically becomes lead 2 or lead 4. Okay, nickel becomes nickel 2. Zinc becomes positive 2, and so on. So that will be very handy in your study of coordination compounds. So for example, cobalt typically becomes positive 3. And the ligands, as we go through the discussion of coordination compounds, we will slowly become more familiar with other ligands. So for now, we see here some examples such as ammonia. So ammonia is a neutral molecule, but it can still be a ligand. And the reason why this has a charge of positive 3 is because the ligands, all of them, 6 of the ammonia molecules, all of them contribute 0 charge. So the net charge of the complex cation is just the charge of your metal center, which is positive 3. This one has a charge of negative 1 because if you can see, what are the ligands surrounding your metal center? You have 4 chloride anions and 2 ammonia molecules. Again, cobalt has a charge of positive 3, and you have 4 chloride ions and 2 ammonia ligands. So get the total, that will give you negative 1. That is why this complex is negatively charged. So that is how you determine the charge of your complex, or how you determine whether it's a cation, an anion, neutral, or if it is a coordination compound. If it is a coordination compound, you must be able to recognize that you have your cation and your anion in your coordination compound. Okay, so for this one, your cation is potassium. You have 4 moles of potassium. And your anion is the complex of iron and cyanide. So cyanide has a charge of negative 1. So the charge of this complex is negative 4. How did I know that? So in your study of ionic compounds back in your Gen Chem in senior high, there's what we call the crisscross method, right? The subscript of your cation is the charge of your anion, and the subscript of your anion is the charge of your cation. So since the subscript of potassium is 4, then the charge of our anion is negative 4. This means the charge of iron here is positive 2 because cyanide has a charge of negative 1. So the net charge of this complex anion is negative 4. Okay? Now, when we study coordination compounds, the number of ligands bound or attached to your metal center is very important. So this number is what we call the coordination number. So this refers to the number of points or points of attachment around your metal center at which bonds with ligands can form. So to determine your coordination number, you simply count how many ligands are there around your metal center. But this is an oversimplification, as we shall see later on. So you just count if you know that the ligand forms only one attachment. That means, okay, one ammonia molecule in this complex forms only one bond with your metal center. Okay? That means there are 6 points of attachments or 6 bonds surrounding our metal center. That gives here cobalt a coordination number of 6. And as we look at the 3 examples here containing cobalt as the metal center, we see that cobalt typically displays a coordination number of 6. So here, how many ligands are surrounding your cobalt? You have 6, 4 chloride anions and 2 ammonia molecules. So that's a total of 6. Again, each of your ligand here only forms one point of attachment or one bond with your metal center. Here we also see a coordination number of 6. You have 3 chloride ions and 3 ammonia molecules. For this one, for the complex part, which is the anion of our compound, the metal center is iron 2 and its coordination number is 6. So here we see some common metal centers encountered in coordination compounds, and we see the typical coordination numbers that they display. So you have copper 1 typically displays a coordination number of 2 or 4, while copper 2 displays a coordination number of either 4 or 6. So what you observe here is that you do not, or it is very rare to see a coordination number of 3 or 5. So typically you will observe 2, 4, and 6, but not 3 or 5. Okay. Now, the typical structures of your coordination compounds or your complexes are shown here. Okay. So if your coordination number is 2, the structure of your complex is linear. If your coordination number is 4, you have 2 options. It can be the square planar or the tetrahedral. And if you have a coordination number of 6, it is the structure is octahedral. Okay. Now for the coordination number 4, so we see that there are 2 choices, either the square planar or the tetrahedral. There's actually no rule. There's no rule that can help us tell whether a certain complex with a coordination number of 4 will assume a square planar structure or a tetrahedral structure. So it's all experimental. You have to perform a certain method for you to determine whether your complex is a square planar or a tetrahedral. Okay. By the way, for the study of complexes or coordination compounds, you have to be very imaginative. So you have to work out your imagination because we will talk a lot about their structures, and you will notice that as we go along our discussion. Okay. So for example, class, here we see a complex anion, and it's asking for the coordination number of nickel in this complex ion and the oxidation state. So for the oxidation number, we count the ligands surrounding our nickel center, and we have 4 cyanide. So we have 4 cyanide ions surrounding the nickel center. So that's 4 cyanide ions and 1 iodide ion. This means the oxidation or the coordination number of nickel here is 5. Okay. Now, what is the oxidation state of nickel? So when you see the term oxidation state, this also refers to the charge of your metal in the compound. So again, the whole complex anion has a charge of -3, and we have 4 cyanide and 1 iodide ions. So that means we have 4 times -1 plus 1 times -1. X here is the oxidation state of nickel. So their sum is -3. So solving for X, that will give you a value of +2. So the answer is the oxidation state of nickel is +2. Okay, next, write the formula of a complex with cyanide ion ligands, an iron ion with an oxidation state of +3 and a coordination number of 6. So this is a very simple problem. You have an iron ion, which means that is your center. And you have cyanide as your ligands. And since the coordination number is 6, then we place a subscript of 6. And don't forget to enclose your ion or molecule ligands in parentheses. So we have to distinguish the ligands, the chemical formulas of the ligands. And then the final objective is to get the charge of this complex. Okay. The oxidation state of iron is +3. We have 6 cyanide ion ligands. Each ligand has a charge of -1. So the overall charge of our complex is -3. So this is how we write the formula of our complex as described. Okay. Now, ligands class, let's talk a bit more about ligands. Okay. So in the formation of your coordination compounds or your complexes, there is another theory of acids and bases that can be used. Okay. So in understanding the behavior of your ligands, how they form this attachment or bond with your metal center, we need to understand the Lewis acid-base theory. So there is another theory. So it defines an acid as a compound that accepts an electron pair. And it defines base as a compound that donates an electron pair. So here we see an example. So this is not a complex, but this is an example of how Lewis acid-base reaction takes place. So you have here a Lewis base, which is a fluoride ion, and you have a Lewis acid, boron trifluoride. This is a Lewis acid because if you notice, boron here does not have an octet of electrons. It only has 6 electrons around it. Bakit 6? So it has 3 bonds, right? 3 single bonds. Each single bond is composed of 2 electrons. Hence, we count the total number of electrons around this boron 6. 1, 2, 3, 4, 5, 6. So it's not an octet, right? And we know that an atom in a molecule, if it is surrounded by an octet of electrons or if it is surrounded by 8 electrons, it's more stable. Hence, this compound, boron trifluoride, will tend to react with a Lewis base, such as fluoride ion. Okay? So this Lewis base will donate a pair of electrons. That's 1 pair of electrons. And it forms another single bond with boron. So this new bond that is formed, the electrons forming this bond both came from your Lewis base. So parang pwede nating sabihin walang contribution yung boron sa paggawa ng bond na to. So it's entirely from your Lewis base, which is the fluoride ion. Okay, so this type of bond is what we call a coordinate covalent bond. So this term applies for Lewis acid-base reactions. So that's what we call a coordinate covalent bond. So again, you have your Lewis acid as a compound that accepts an electron pair and a Lewis base as the one that donates an electron pair. So using this concept of Lewis acids and bases, then we can describe how complexes are formed. So what actually happens is a Lewis acid-base reaction. Your metal center acts as a Lewis acid, and the ligands act as Lewis bases. Now, since your metal center is charged, so they are cations, they are positively charged, that also drives the affinity of your ligands. So in this example, we see cobalt-3 as our Lewis acid, and we have 6 ammonia molecules acting as Lewis bases. If you recall, ammonia molecules or an ammonia molecule has a lone pair of lone pair of electrons. So this is the one that it donates to the metal center to form that attachment or that bond. Okay, so each of your ammonia molecule donates one pair of electron to form a bond with the metal center. So here we see that the process by which your complexes are formed is a Lewis acid-base reaction. Your metal center is the Lewis acid, your ligands are the bases. Okay? Now, if you recall, a few slides back, I mentioned that the ligands that we have seen so far make only one bond. So for example, here, each ammonia molecule forms one bond, right? So such ligands are described as monodentate. So monodentate monodentate ligands are those that use one pair of electrons to form one point of attachment with your central metal or ion. Okay? So again, each ammonia molecule forms one bond with your metal center. You have 6 ammonia molecules, so you have 6 bonds around your metal center. Now, aside from monodentate, we also have polydentate. Okay, so when we say polydentate, it's a ligand that uses more than one pair of electrons to form more than one point of attachment with the central metal or ion. So before we get overwhelmed, so how does a polydentate attach itself to a metal center? Let's look first at some common monodentate ligands. So we've seen ammonia, we've seen our halides, your halogens with the negative charge. So other examples, if you see here, we can classify our monodentate ligands as either neutral or anions. But we don't have cation ligands. Why? Because your ligand must be a Lewis base. So again, Lewis bases are electron pair donors, right? So anions are good Lewis bases because they have an excess of electrons. These neutral molecules are also good Lewis bases because they have lone pairs of electrons that they can use to form that attachment with your metal center. Water, so we see here water, ammonia, your carbon monoxide, nitrogen monoxide, methylamine, pyridine is, I think, is a new molecule for you, but it pays to know its chemical formula, C5H5N. And you have your anions, your halides, oxide, hydroxide, cyanide, sulfate, thiosulfate, nitrite. This is nitrite, but with a different orientation. It's the same molecule. Thiocyanate, and also thiocyanate with a different orientation. Now here, you observe that they have names as ligands. We will use this when we go to the nomenclature of your coordination compounds. So hang in there, okay? Just acknowledge that these ligands have names or special names if they are part of a complex. So now let's go to our polydentate ligands, okay? So there are three examples here. We have ethylene diamine. So there's the structure. Okay. And the lone pairs of electrons used for the bonds or the attachments with the metal center are shown in the drawing. So you have there two lone pairs. That means one ethylene diamine molecule forms two attachments with your metal center. So we can say that it's a bidentate. It's a bidentate ligand. Okay. Ethylene diamine as a ligand has an abbreviation. So that's EN. So it also pays to know this abbreviation of your polydentate ligands. This is helpful in writing the chemical formulas of your complexes. Another example is oxalate. So its name as a ligand is oxalato. This one is also a bidentate. So even if you have the lone pairs drawn there, it's just a bidentate ligand. So it's because of the orientation of the oxygen atoms, okay? So the oxygen atoms that form attachments with a metal center are the negatively charged oxygen atoms. So these neutral oxygens do not form attachments. Hence, oxalate is just a bidentate ligand. And then the third example here is EDTA. Sometimes you call it EDTA. So its whole name is ethylene diamine tetraacetate or tetraacetic acid. Its name as a ligand is ethylene diamine tetraacetato. And its abbreviation is EDTA. So, how many points of attachment can EDTA form? 6. It can form 6 points of attachments. So the atoms involved in the attachments are these nitrogens with their lone pairs and your negatively charged oxygens here. So it means that if your metal center has a coordination number of 6 and it's coordinated with EDTA, then it means one EDTA molecule forms a complex with a metal center. Kasi isang EDTA, 6 points of attachment na eh. Right? Okay. So here, class, we see here a specific example. We have platinum 2 as the metal center, and it's surrounded by two ethylene diamine ligands. So you see here the abbreviation was used in the chemical formula. So if you see EN, that's ethylene diamine. It has a subscript of 2. That means there are two ethylene diamine molecules bonded to your metal center. And here we see how the ethylene diamine molecules are oriented around your metal center. Okay? Now, if you notice, class, so this is your metal center. So there's a bond here with nitrogen, and then you have the ethylene diamine molecule. And then this nitrogen is bonded to your metal center as well. So here we observe that there is a ring structure that is formed when your ethylene diamine ligands interact with your metal center. There are actually two rings in the structure of this complex. So this is the first ring, the one that I drew with the red color, and this one is the second ring. It's a pentagon, right? The ring has 5 sides. That's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So this, the reason why I'm telling you this is because there is a special term used to refer to complexes with rings in their structure. So this is typically observed with polydentate ligands. Of course, you will not observe this with monodentate ligands. So that term is chelate. Chelate. So if you have a complex that has rings in its structure because of your polydentate ligands, you can refer to this complex as a chelate. And you can use the term chelating agent to refer to your polydentate ligands that produces a chelate with your metal ion. So the process is called chelation. So it's not chelate, it's chelate. Okay? So you might be wondering how or what is the structure of metal edta chelate or metal edta complex. So you have your edta here, a simplified structure. So each point here, you have carbon there, okay? And then, again, the points of attachments are your nitrogens and the negatively charged oxygens in EDTA. So here you see that one EDTA molecule forms a complex with a metal center giving a coordination number of 6. So we can also describe EDTA as a hexadentate ligand. Okay? EDTA is a chelating agent. This can also be called a metal EDTA chelate. This reaction shown here is a chelation process or a chelation reaction. Okay? So you see there the points of attachments, how the EDTA is oriented around, or how EDTA folds itself around the metal center to form this complex or chelate. Now, class, while we are talking about EDTA or EDTA, one of the applications of your chelating agents, specifically your EDTA, is in metal poisoning. Okay? So typically, the first response or the first aid for a person that was poisoned with metal is ingestion of EDTA or EDTA, because your EDTA can form these chelates with the metal that is inside the body of the patient, and then that protects the cells of the patients from attack by your metal ions, the poisonous or the toxic metal ions. So once the chelate, the EDTA chelate forms, it can easily be flushed out through the excretory system. And then one more application of your EDTA is in food preservatives. So if you try to look at the ingredients of some of the products that you have in your pantry, I think mayonnaise. If you look at the ingredients of mayonnaise, you will see there EDTA. Okay. The reason why they use EDTA as a preservative or to prolong the shelf life of these food products is because EDTA can form these complexes with metals, and for some bacteria, these metals are important for them to thrive. But since EDTA forms these complexes, the metals are no longer available for the bacteria. So that lessens the chance of bacterial growth in these food products. Okay. Okay, so I will end the first video on coordination compounds here. In the next video, you will learn how to name your complexes or your coordination compounds.